All right, so I'm going to go in grueling detail, step by step, through the Unit 7 practice test because I notice a lot of people are still struggling with writing balanced reactions and being able to do the stoichiometry that you're being asked to do. So I need you guys to sit through as I'm talking. Feel free, please correct your Unit 7 practice test so you have the correct work. Feel free to pause me whenever you need to, but I'm going to move on. All right, so let's do this. For 1A, it says write the balanced reaction below. So you've got chromium reacting with oxygen. So you're going to write just chromium reacting with oxygen. Keep in mind, oxygen is one of the diatomic elements on your periodic table. If you look at your periodic table, starting with nitrogen, you make that 7, right? Nitrogen, oxygen, fluorine, chlorine, bromine, iodine, that's 6, and then hydrogen's the 7th one. So what it means to be diatomic is instead of existing just as O, it's going to exist as O2. So you all have written Cr plus O2, and that produces my product. My product is chromium 3 oxide. That tells me the charge of chromium is 3 plus, the charge of oxygen is 2 minus. So when I cross my charges, I get Cr2O3, okay? And then I need to balance. So I've got 3 oxygens here, 2 here, so that's why I put a 2 in front here, a 3 in front here. That gives me 6 oxygens on both sides. And then I have 4 chromiums, and I am balanced. Next problem. How many moles of oxygen react with 4.50 moles of chromium? So I start with my given, 4.50, and notice I'm showing all of my units, moles of Cr. I'm going to crisscross swoosh. On the bottom, I want to get out of moles of chromium, so I put moles of chromium on the bottom. And I want to get into moles of oxygen, so I put that up top. Here, when you have a mole-to-mole ratio, when you're going from moles of one entity into moles of another, you need to use coefficients. So you've got a 4, a 3, and a 2. So the coefficient in front of moles of oxygen is a 3. The coefficient in front of chromium is a 4. So I take 4.50, multiply by 3, divide by 4, and I get 3.38 moles of oxygen because I am rounding to 3 sig figs. Okay, so copy all of this down as you're going so you have the correct work if you still didn't have the correct work. Next, you're going to allow 74 grams of chromium and 62 grams of oxygen to mix together. So I have 2 different amounts of reactants. So that tells me that this is going to be a limiting reactant problem. Okay, so I start with 74.0 grams of Cr, and I need to get that into grams of, and this should not be Cr3O2, it should be Cr2O3. So I'm going to start with grams of Cr. In order to get into grams of Cr2O3, I got to first get into moles of Cr. So I put grams of Cr on bottom, moles of Cr up top. Then I'm going to get out of moles of Cr by putting it on bottom and into moles of Cr2O3 up top. Okay, I'm going to keep going. I'm not going to talk about the numbers yet. Then to get out of moles of Cr2O3, I'm going to put moles of Cr2O3 on bottom and grams of Cr2O3 up top. When you have grams per mole, that tells you that you need to find the molar mass of that substance and put the molar mass in front of grams. So the molar mass of Cr is 52.00 grams. And then it's for every 1 mole. So I put 1 mole of Cr on top. Here, when you have a mole-to-mole ratio, you're going to simply use the coefficients. So there's a 2 in front of Cr2O3 and a 4 in front of Cr. And then here you've got grams per mole again. So now you need the molar mass of Cr2O3. So what you're going to do to determine that molar mass, take the molar mass of chromium, 52, multiply by 2, and then you are going to add to that the molar mass of oxygen, 15.999, and multiply that by 3, and you get 151.997. So I'm going to take 74, I'm going to divide by 52, multiply by 2, divide by 4, then multiply by 151.997, and I get 108 when I round to 3 sig figs, 108 grams of Cr2O3. I don't know if that's my answer yet, okay, but that's one of the masses. That's the mass that 74 grams of chromium can produce. I then look at oxygen, 62.0 grams of oxygen, and again, I need to get into grams of Cr2O3. So to get out of grams of oxygen, I put grams of oxygen on bottom, moles of oxygen up top. To get out of moles of oxygen, put moles of oxygen on bottom, then I can get into moles of Cr2O3 up top. Then finally, out of moles of Cr2O3 into grams of Cr2O3. All right? Again, you cannot go directly from grams of O2 into grams of Cr. You got to get to this mole-to-mole ratio to be able to get out of terms of O2 and into terms of Cr2O3. So here again, grams per mole, I need the molar mass to be put in front of grams. So a lot of people made the error of just putting 15.99. Keep in mind, oxygen is diatomic, so you got to multiply the 15.999 molar mass by 2. So I get 31.998. The coefficient in front of chromium oxide is a 2, in front of oxygen is a 3. And then the molar mass again that goes in front of grams for Cr2O3 is the same as it was above, 151.997. So 62 divided by 31.998 times 2 divided by 3 times 151.997 grams. And the answer I get rounded to 3 sig figs is 196. Okay, so here's where the logic comes in. If you think about it, okay, chromium can only make 108 grams of chromium oxide. Oxygen can make 196. So this is like the s'more example, right? I can have 100 marshmallows, but if I only have 4 pieces of chocolate, I can only make 4 s'mores. It doesn't matter that I have plenty of marshmallows. Same thing here. Even though I have plenty of oxygen, so it could make up to 196 grams of product, since my chromium can only make 108, my chromium, Cr, is my limiting reactant, and oxygen is my excess reactant. Okay? So make sure when you're doing this, you've got to box your answer. So you're going to box 108 grams because that's the amount that can actually be, theoretically, should be produced, not 196. If you box both answers, I cannot give you full credit. For II, it says, what is the percent yield of Cr2O3 for this reaction? So remember, percent yield is your actual divided by your theoretical. Actual is what you actually get in the lab. So I would have to tell you that on a quiz because you're not in a lab. So I tell you at the beginning of the question that 87.3 grams are actually obtained. So you're going to have 87.3 grams on top divided by, theoretically, how much should have been produced? 108 grams. And then you're going to multiply by 100. So 87.3 divided by 108, and I get 80.8%. Okay, 3 sig figs. All right, molarity. Remember, molarity is a measure of concentration, and it is the moles of your solute divided by liters of your solution. Okay, so the molarity here, it tells me I have a 0.512 molar solution, so I know the molarity, and it gives me the grams of my solute. Well, that's great, but I can't plug grams into my amount of solute. I have to get into moles. So I'm going to start with 0.325 grams of NaI, and I'm going to get into moles. I put grams on bottom, moles up top. Remember, gram to mole, I need molar mass. So the molar mass of NaI goes in front of grams, so 149.9. So I'm going to take 0.325, divide by my molar mass, and I get 0.002168. So what I get is 0.512 is the molarity, molar, equals my moles, 0.002168, divided by my volume, my X. To answer this question, a lot of people will just multiply these two values together and call it a day. That is incorrect. What you need to do is take 0.512, multiply by X, set that equal to 0.002168 times what 0.512 is over, which is a 1, because you're cross-multiplying. So I get 0.512 times X equals 0.002168. I divide both sides by my 0.512, and I get 0.00423, or if you want in scientific notation, 4.23 times 10 to the negative third, and my units are liters. You can always convert this into milliliters by multiplying by 1,000 if you want, but I just didn't stipulate, so you don't need to. All right, for number 3, it asks what my molarity is, and it tells me I dissolve 10.7 grams of NaI in a solution that has a volume of 0.250 liters. So I start with 10.7 grams, and I'm going to convert into moles. So grams on bottom, moles up top. The molar mass of NaI is 149.9 grams. So I'm going to divide, and I get 0.07138 moles for every 0.250 liters. I divide, and I get 0.268, so I round to 3 sig figs, molar, capital M. Last question here. All right, I've got 2 different solutions, and I add 1 teaspoon of sugar to each of them, right? And it dissolves perfectly. Okay, awesome. I now have 2 beakers, each full of water with 1 teaspoon of sugar dissolved. Cool. I then add another teaspoon, okay, and stir, and all the sugar dissolves. So what that tells me, since I can add more sugar, I can dissolve more sugar into these 2 solutions. That tells me that these solutions right now, before I added the sugar, were both unsaturated, right? Because you can still dissolve more. Then I've added the sugar, so I now have two teaspoons in there, and I've mixed them, okay? Then it tells me for beaker A, I add 1 more teaspoon, and even after stirring, there is exactly 1 teaspoon of sugar at the bottom. So what that tells me is I could not add any more sugar to this solution, okay? So since I can't add any more sugar, it is just going to settle at the bottom. That means that this solution here is saturated at this point. It has the maximum amount of solute dissolved, and it will remain saturated, right? If I keep adding solid, it's just going to sink to the bottom. No more is going to dissolve. For this one, okay, if you notice, because you did the exact same thing to beaker A, B is also going to be saturated. But now what we're going to do is we're going to leave this solution, and we're going to allow some of the water to leave. And if you notice, you have a maximum amount of solid dissolved, but then you remove some water and none of the solid leaves. So your concentration, even though it shouldn't be able to, it went up. Just like when we heated the rock candy solution, you were able to dissolve more sugar than really should have dissolved in the solution. You have now created, either by removing the water or heating up the water like you did in the lab, you have created what we call a super saturated solution. It has more dissolved than really should be dissolved, should be allowed, okay? So if I went through this and you just scribbled and didn't pay attention, go back, rewatch these explanations. Your test is going to look almost identical to this, okay? When you are done with this, once you've corrected all of your work, it is all correct, you're confident with it, you're going to resubmit this onto Schoology. That is your task number 1. When you've done that, then you are going to go onto your Schoology. And on your Schoology, you're going to go to today's folder, okay? And you are going to click on another Unit 7 practice test. And what you'll notice is you have another opportunity to practice this. New reaction, new numbers, same concepts. Okay, so until I join and send you to breakout rooms, if you've already watched this video and you're good with Unit 7 practice test, you've corrected it, you've resubmitted correct work, then you can start working on this. And then I'm going to send people to breakout rooms once I rejoin your class.